Hello, fans of parametric methods. We have a continuation of the previous video where we had the simple portal frame with a roller on the right side and a pin on the left side to keep it statically determinate. But the new feature here is that we have a point load somewhere on the beam going down, but we also have that a fraction of that load going sideways. And we can control that fraction by a slider here. I made it 50%, 50% of the gravity, or 40% of the gravity, or 30% of the gravity as an equivalent lateral static load. Let's say 50% of the gravity load is being applied to the diaphragm, really, but it's a beam here, but we don't hit the columns. The nice thing here, I think, is that we can set up two load cases, and we could look at load case 0, which is the lateral load, and we can get the displacement here, which is about 3/4 of an inch. You could see that here, 0.76. And then we could switch that to load case 1, which is the gravity, and we see the second number, 0.44. So I played with the geometry so that we have reasonably the same magnitudes of displacement. Now let's take a look at the bending moment diagrams. And this, I think, again, is very telling, right? That for the roller pinned case, there is no bending in the columns. There can't be, because there's no horizontal reaction here. So there's no bending up that right side. And if there's no horizontal loads, then the horizontal reaction is 0 on the left-hand side. And we can get the magnitude of the bending, which I think is in kip feet, according to Clemens here. But let's look at the other load case now, and we have something different, right? We have the lateral load going sideways, and notice I put it at the center of the diaphragm. You could put it at the joint of the beam column interface, but I like putting it at the center of that beam, which I'm calling diaphragm in 3D, correct? But here we do have bending now because the horizontal reaction at the left pin has to equilibrate that lateral load, but it is pinned down there, so we start at 0, and we move up to 7.6, and then we match 7.6 on the beam interface or the diaphragm interface. Now, one more super fun thing that we could do is we could look at different boundary conditions. So suppose that both sides are pinned. Well, what does that mean? Both sides are pinned. So we don't have any translation at the bottom. So let's look at the deformations first. The magnitudes are pretty small here for the deformations. We can get the numbers here. Why is it smaller? It's a stiffer structure, so we have more energy required. But let's crank up the deformation, and you could see that the column is bending because it's restrained here. Super nice, right? Let's look at the bending moment diagram for that one then. And it's just like you'd expect it to be: positive and negative curvature with an inflection point, which could be utilized if you were a clever designer like Robert Maillard, or genius, sorry, not even clever. And then let's go back to this load case. Now here again, the lateral load is on the side, at the center of mass of the diaphragm, let's say, and we have bending in here, right? So let's click on that. And that looks, I think, great, right? And then finally, we can fix the base completely. Let's fix the base completely. There it is, fixed on the right side. And now it will be fixed on the left side. And you could see that you have bending moment at the bottom, bending moment at the top. Let's just look at the numbers really quick again. For no rotation, we had 3 point, for no rotational restraint, excuse me, we had 3.8 kip feet. And notice what happens here, dropping down about half, right? Half of that moment. But now the penalty, of course, the energy has to go somewhere. The penalty is that we have to restrain the moment at the base. And if that moves a little bit, then it's not restrained. If it moves a little bit, it's not restrained. So really, I think super fantastic ability to quickly assess your design decisions and look at the numbers. And, maybe we'll show you how to do this in Python next time, or show you how to set up the model, but this is the guts of it. Okay. Hope you loved it. Please like and subscribe.